last time. So this is the so-called Redfield equation in operator form, in which we have the first part would just be the usual evolution under H0 with isotropic Hamiltonians. And then gamma is the relaxation superoperator defined here. And little j is the real part of the power spectral density function, where f are the stochastic functions. So the j is the real part of the Fourier transformation of the autocorrelation function of f. And then I said very quickly, as always, we can expand the density operator in terms of basis operators, in which the coefficients are given by this trace operation. That goes back to one of the early lectures. So that if we make the substitution and collect the terms, we then have algebraic equations, a set of coupled differential algebraic equations, in which omega mn are precession frequencies. We know that they're precession frequencies because they have an imaginary factor in front of them. And we also have cross-relaxation rate constants defined by this expression. So these capital omegas, for example, could be the chemical shifts. They would also be J couplings. So for a chemical shift, M and N would be identical. And for a J coupling, M and N would refer to the two coupling factors. Here for relaxation rate constants, if M and N are the same, those are just auto-relaxation rate constants, things like R1 and R2. And if M and N are different, these are cross-relaxation rate constants, reflecting exchange between different sets of basis operators representing different coherences. And we remember when we only have a single sum here over P, that this expression applies the secular approximation. So cross-relaxation is only allowed between operators that have the same eigenvalues. And we can write this in matrix form, which is particularly convenient then for computer calculations. So we have, like I said, a set of differential equations that are algebraic. These are just the amplitudes then of the different operators at some point in the pulse sequence. Here are all the frequencies, here are all the rate constants. And in principle, this is just a big matrix differential equation that Mathematica could easily solve for us quite back to doing numerical calculation. You can also notice that if we had two spins, like the dimensionality of the density operator would be 2 by 2. There are 4 elements in the density operator. So that we could always have a basis of 4 operators to represent any arbitrary density operator. And that means that, for a single spin, the density operator is a 2 by 2 matrix. For 2 spin 1/2 particles, the density operator is 4 by 4. And we could represent that operator as some combination of 16 basis operators. The basis operators being things, the product operators, things like IX, SS, 2IX, SZ, IX, SF, so on and so forth. And that means we have 16 by 16 possible evolution frequencies and relaxation rate constants. And in this formulation, we would have listed in a column vector the amplitude of those 16 basis operators This then is a 16 by 16 matrix. It might have a lot of zeros in it. This is a 16 by 16 matrix. It might have a lot of zeros in it. If we went back to the block equation, just have a single spin 1/2 particle, we would have 4 basis operators. The identity operator Ix, Iy, Iz, which would be arranged in this column. I mean, usually we forget about the identity operator, but we don't have to. So this formulation looks completely isomorphous to the block equation. It's just that the column vector is longer and these vectors are longer because we have more basis operators to keep track of them. But that's a nice reason to convert the operator form of the equation into the algebraic form, because we get back to something that looks very much like the block equation, where we have a matrix differential equation with some convolution coefficient and some damping. And if I put in here Ix, Iy, Iz, this formulation with its collateral factor block equations. So here's a very compact notation in which I write everything in matrices. This term is a bit inconvenient, right? This is the term that drives the system back to thermal equilibrium. And it's possible to patch the equations up by defining a thermal equilibrium operator. That was done, it's been done over and over again. I think Engineer had a paper about this more recently, Malcolm Levitt, and Ronnie Roche, who's here at City College, has been interested in dealing with this sort of reformulation of the equation, in which this term essentially gets incorporated into an expanded set of matrices here. I'm not going to say anything more about that, but if you're interested, you can drop Ronnie in here and we'll talk about it. So again, most of the time in relaxation theory, we're primarily interested in understanding things about J. The rest of this are just computations of spin operators, and the spin operators don't change from protein to protein or molecule to molecule. They're just set by how many spins we have, whether they're spin 1/2, spin 1, etc. So these all just need to be worked out once in all of history. But the J's depend on the details of the molecule. So J is much more interesting. So it again is the real part of the Fourier transform of the autocorrelation function of the F's. And at least in solution, and next time we'll talk a little bit about solid state and about relaxation. So if there are exceptions, you can help you. But at least in solution state, the F's always can be written as some function that contains a bunch of physical parameters, bond lengths, chemical shift anisotropies, etc. And then spherical harmonics that depend on the angles orienting the tensor, describing the Hamiltonian, whatever Hamiltonian we're talking about. The tensor representation orients that in the laboratory. And you know from band that these Hamiltonians or tensors all have their simplest representation in the principal axis frame, and then one can do transformations from the principal axis frame to the molecular frame to the laboratory frame. K here is the rank of the tensor, and in solution NMR, these are normally 2. K is 2, sometimes 1 or 0, but not higher than 2. So we'll theory would be more general. But if we're talking about rotational diffusion in proteins, for example, as measured by NMR or by fluorescence spectroscopy, for example, then the spherical harmonics are all around too. But if you measure rotation from some other measurements, like the linear microwave experiment, it turns out that the theory ends up with rank 1 spherical harmonics. And that ends up being what we call the rotational correlation kind of differs. And that's sometimes causes people to make mistakes when they're comparing different techniques, because the rotational correlation kind that comes out of the two experiments is different, but that's just the trivial property of the spherical harmonics. So this repeats what Ann told you. We can transform the spherical harmonics using linear rotation matrices from one frame to another. So again, from a principal axis frame to a molecular frame or to a molecular. So if we substitute in, then we have, quite trivially, this correlation function. And it's quite common to assume, in order to make any progress, that the fluctuations affecting whatever's in this function C is independent of the reorientation. So that this autocorrelation function of 4 terms can be split into the product of an autocorrelation function for the C's and an autocorrelation function for the Y's. I mean, that's a convenient approximation just to get on to some actual formula. But it's easy to imagine violations. So we took the case of dipole coupling between pairs of hydrogens. This angle would represent the angle that the vector connecting the two hydrogens made relative to the laboratory frame. And C here would contain things like 1 over r cubed, where r was the length of that vector, and then magnetogyric ratios, etc. All the other parts of the dipole coupling are constants. But of course, as the molecule is moving around, if the shape of the molecule is changing so that the bond length, or not the bond length, but the distance between the hydrogens was varying on the same time scale that the molecule was tumbling, then you might not be able to make this partition into 2 separate correlation functions. You might have to calculate the full joint correlation function. And that's pretty much impossible to do analytically. That means mostly that you have to run some computer simulation so that you can simulate the autocorrelation function. Fortunately, for structure determination by NMR, where you rely on the NOEs between protons, it turns out in many cases, although not all, in many cases that the effects on relaxation from the distance fluctuation tend to offset the effects from the angular fluctuations. Raphael Ruschweiler showed this when he was a postdoc by doing computer simulations. So just by luck, the problem isn't as bad as it might be. And then, since the dipole coupling goes as 1 over r cubed and C's appear twice, the relaxation will depend on 1 over r to the 6th. So that if you're getting a distance constraint out from the NOE, when you take the 6th root, the errors get much, much smaller. So the errors that come from having to make these approximations end up influencing the result less than you might think most of the time, but not always. But we'll assume that we can do this so that actually this is a typo. This should still be inside the integral, just now separated from the line. Fix that. But then this part is called the orientational spectral density function, usually called capital J. So the Fourier transform of just the autocorrelation function of the spherical harmonics will be capital J in most maximums. Okay, so let's come back to this mistake here. So first we're going to say this is independent of the y's. And so that I can put angle bracket here, angle bracket here. So one situation would be where these were constants. If C was a constant, then I can factor this out. The other two limits would be, suppose the time variation in the C's was very fast. In that case, the autocorrelation function would decay very quickly to whatever its limiting value was. And the limiting value allows me to average separately over each C. So I would get the square of the average of the C's. So think about bond vibrations. The bond vibrations are on a femtosecond time scale. Tumbling is on a nanosecond time scale. So the autocorrelation function for the bond vibration will have decayed to a plateau long before the molecule has tumbled. So that I can replace this then with the square of the average of C of T. And if this is the dipole coupling, the C would depend on 1 over R cubed, so I would end up with the square of the average of 1 over R to the cube, being the important part of relaxation. And that's actually led to a lot of trouble, because the average of 1 over R to the cube, of R cubed, is not the same as the average of 1 over the average of R cubed. And this is not the same as this. And if, for example, you look at a crystal structure and measure, and in the crystal structure figure out what the bond length is, that is something like this. Just in the crystal structure, you have something like this, where the averaging is over the vibration within a crystal and any variation from asymmetric unit to asymmetric unit. So it's one kind of averaging that comes out of crystallography, and that's not going to be the kind of averaging that comes out of NMR. And if you do neutron scattering, it's yet something else. So figuring out what bond length, suppose we're trying to use, as is very common, NH relaxation, N15 relaxation, we need to know the bond length, what bond length to use for the nitrogen amide hydrogen bond length. And it's not so obvious how one does that. There have been a couple of choices made over the years, and one always has to be careful. Essentially, it turns into a scaling property, but one always has to know what the authors of the paper use. The other limit would be variation here is very slow compared to tumbling. in which case we can just call this the square of C of t, essentially the same as making tau 0, so that we have the mean squared C, and that would mean we would end up with the average of 1 over r to the 6th, rather than the average of 1 over r cubed squared. And that's also different. So here, if C of tau is fast compared to tumbling, we end up then with the average of C of tau squared, and if it's slow, we end up with the average of the square of C of tau. For the dipole coupling, this would be 1 over r cubed average squared, and here it would be the average of 1 over r to the 6th, because the dipole coupling goes 1 over r cubed. And these aren't going to be necessarily the same thing. So those three cases are shown here. So if C is constant, we just add C squared j omega. For slow variation in C, we have the average of the square of C, and for fast variation in C, we have the average of C squared. This comes up again commonly in structure calculations because, for example, methyl groups, the 3 hydrogens are rotating very fast compared to tumbling. So you only see one resonance line for the methyl protons, but if there's a hydrogen sitting here and you want to know the distance, you're looking at the NOE, the distance from this hydrogen is different to the 3 hydrogens in the methyl group. So how do you average that together? There's only one signal. So you only measure one NOE, and you have to know how to average it. And this is sometimes done crudely, but the right answer is these tumble rapidly, so we should be averaging the 3 distances as 1 over r cubed and then squaring. So some structure calculation programs have the option to turn on r to the minus 3rd averaging, meaning the methyl groups will be treated in this way, in which the 3 distances, 1 over r cubed, the 3 different distances are averaged, and then that's squared in calculating the NOE. The other limit might be applied to aromatic rings limits. Most aromatic rings, if you think of a phenylalanine, for example, the there's 2 delta hydrogens, but you normally only see one signal. The ring is flipping fast enough to average the 2 sides, even though they're in different environments and may have different chemical shifts. The ring is flipping fast enough to average them. There are some exceptions, particularly cool molecule now. But if on the chemical shift time scale, the ring is flipping fast enough to average the resonances, that can still be slow flipping on the tumbling time scale, because the chemical shift time scale is going to be on the order of microseconds. Tumbling is nanoseconds. So when you see single resonance line for the symmetry-related hydrogens, say a phenylalanine ring, one interpretation is that the flipping is slow on the tumbling time scale, and therefore, if you're calculating the NOE to this hydrogen, you should average the 1 over r to the 6th distances to the 2 symmetry-related hydrogens out to the remote hydrogen. And then some structure calculation programs have in them an option to do hardly like the sixth averaging, which would then be applied to the aromatic symmetry or the aromatic. And then anything in between these three limits, as I said, basically requires computer calculations. It's too complicated to try to figure out usually the joint probability, non-dependent probability distribution for the fluctuations in C as well as the fluctuations in orientation. This also then is popular if we're thinking now just about the orientational correlation function. It's popular to factor that into a contribution from overall coupling and a contribution from any internal motions. So this factorization is perfectly fine if the timescales are separated enough. And if you imagine that the internal motions are independent of the overall motions. The latter isn't so easy. It's easy to imagine, for example, if you have a protein, an enzyme like a venylate kinase that is a clamshell that can open and close. It may well be that the overall coupling properties of the molecule are different, whether it's closed or open. And if the opening and closing is on the same time scale as overall coupling, then you're not going to be able to make this kind of factorization. There's relatively little known about what to do in these cases where you can make the separation. There is some work by Dave Case kind of started, and then David Cushman's group has done some work together, some of it with Marius Floor. Or my group built a little bit on that kind of work, but it's still, if you went to data processing programs that are analyzing relaxation data, this problem of non-factorization, I don't think exists in any packages available for analyzing it. We can always assume this factorization works. So we already did the spherical molecule. And for a molecule with axial symmetry, the problem is relatively easy to solve. You end up with three different rotational correlation times. The correlation function has three exponentials, and those exponentials are weighted depending on the orientation that the particular bond makes or interaction makes in the laboratory frame. So this actually is really useful because, again, if we took the example of nitrogen-15 relaxation, then the dominant interaction is the dipole interaction between the nitrogen and the attached hydrogen. And that orientation is basically the orientation of the NH compound. So we more or less know what that is. In a typical protein, though, a folded tertiary structure, the NHs point in a number of different directions. And that means that we know the structure, we know these thetas. We can relate the orientation of each individual bond vector geometrically to the principal axis frame of the diffusion tensor. So that while this looks like it would have a large number of parameters, we would have the Euler angles orienting the diffusion tensor principal axis system in the lab frame. That's what's kind of as the molecular compass. And then we have the different diffusion tensor components, the principal axis of the diffusion tensor. the principal value of the fusion tensor. So it looks like a lot of parameters, but the problem can be highly overdetermined because we might have 100 or more NH vectors pointing in different directions. So N15 relaxation turned out to be a very powerful way for characterizing rotational fusion in this sector. There can be problems. For example, take a 4-helix bundle probe. In a 4-helix bundle, where do all the NHs point? Anyone know what a 4-helix bundle looks like? Basically 4 parallel helices. So where do all the NHs point in the helix? Where do the NH vectors point? They all point along the helix axis by and large. So in a 4-helix bundle, more or less, all of these angles are the same. And you don't get a distribution of different orientations to help sort out the values of this equation. So then what might you think of doing? You have to find some other relaxation vector, right? Some other relaxation interaction that points in a new direction. And one possibility that isn't so widely used, because the experiment is more difficult, would be the C13 alpha relaxation, because in the helix, the H alpha, the NHs point along the axis, and the H alphas point orthogonally to the axis of the helix. So then you solve the problem. And David Kober, Ronnie Roche, David Frischman wrote a paper some time ago about the sampling properties of vectors in the sphere, where you can analyze that from the structure, how good a job you're going to be able to do in covering the sphere and getting good estimates then based on the distribution of the NHs, etc. This problem, by the way, reappeared and was more or less solved completely independently, I think, for RDCs. The same problem that comes up with RDCs. You're trying to use RDCs to characterize structure or dynamic model. You have the same issue. They all point in the same direction. Then additional spins on providing really new information. And with RDCs, the NHs aren't helpful enough. And then you try to measure other couplings, usually being affected on the plane. Unfortunately, it's somewhat easier to measure more dipole coupling, residual dipole coupling, than it is to measure more relaxation. Right. So that was, and that's what I meant, that the problem of RDC was resolved, already been solved. It's the same thing, it's the same problem for relaxation.
Different media, but I wonder why I want to try other form vectors.
Well, people do both. Look at them. I mean, the only headache is you have to make double label, triple label protein here and measure the coupling. But certainly for using RDCs to study conformational fluctuations, having other vectors in addition to the media is really helpful in trying to characterize, for example, movement of the peptide.
Experiments themselves are helpful.
there's just examples for 3 bonds oriented at different angles in the molecule for, I just picked some degree of anisotropy just to show you that the correlation functions differ depending on orientation. And before you transform these dots, the spectral densities would differ, and therefore the relaxation was different. These experiments are precise enough anyway that proteins the size of 150 residues or so, one can detect deviations from the molecule being isotropic of a few percent. They're really very, very sensitive experiments. I won't really say anything else about it. You can go read Raphael's papers. In the fully anisotropic case, the equation will get to be extremely complicated. There are then 5 different correlation times, all weighted together with very complicated functions of the angles. The Raphael showed that if you had a moderate degree of anisotropy in the diffusion tensor, then you could treat the problem as if each spin behaved isotropically. But the isotropic correlation time you would measure would be a function of the angles that local diffusion tensor, or that local bond vector made with the diffusion tensor. And he showed that there was a very simple way that solving for the diffusion tensor with that approximation. So here's just an example where I did some exact calculations and then his estimation, the agreement. I don't know what is the agenda.
Black one.
Maybe. Anyway, there's exacted isotropic variant underneath here for 0 degree orientation and 90 degrees. There's a little bit of deviation. I just mentioned this so you know that this local isotropic approximation exists. Raphael managed to write a science paper. Both remarkably clever analysis and remarkable paper writing, and the paper about this kind of theory and the science. Now, the internal motions on the time scales that we're interested in, by the time we get out to picoseconds, as far as I know, there's little evidence for any underdamped motions in proteins or other biological macromolecules. Maybe Anne wants to weigh in on that. But to the extent the motions are overdamped, then the internal correlation functions are going to be sums of exponentials. And if the internal motion is restricted, then that internal correlation function is going to come down to some plateau is not going to be 0. And in NMR, that plateau is called S squared, or the square of the generalized order parameter, an idea thought up by Lopari and Novel a long time ago. So that this could be rewritten with the n0 is 0 for infinite. So then we can the sum is n equals 1 alpha some number. We have a set of a sum of exponentials that decay to a plateau. And this is an out-of-distance straight line. S squared has a formal definition that comes from the properties of the autocorrelation. At long times, the autocorrelation function becomes the square of the mean of the individual spherical harmonics, and then use the spherical harmonic closure theorem and this formal expression S squared, although frequently people don't bother writing it down. So S squared then is a measure of the average, i.e. equilibrium distribution of the orientation of whatever interaction we're talking about, the non-vector orientation, etc. So it's an equilibrium property of the molecule in the system. It's not dynamics. People call S squared dynamics all the time. NMR spectroscopists call S squared dynamics, but it's not dynamic at all. It's the equilibrium distribution of, say, bond vector orientation. So NMR sloppiness drives physical chemists crazy. So if you're talking about physical chemists, you probably have to keep in mind that S squared is a measure of the equilibrium distribution of orientations of some vector. Here are some pictures. S squared for a rigid site is 1, and then it tends to decay away. There's two simple models. The fusion in a cone is really what's pictured here. The vector can freely move within a cone, but can't leave the walls. And then this Gaussian axial fluctuation model is again used to Raphael Bruchweiler. In that model, the vector is moving on the surface of the cone at fixed angles, just going around on the surface. And then there's some standard deviation for the angular fluctuations around the surface of the cone, but it can't go into the cone. But the main point is the order parameters get smaller as the degree of disorder, or the degree of larger and larger angular orientations that allow the order parameter to get smaller. These days, it's popular to analyze the order parameters by simulation. You can easily calculate them in simulations. But the real problem is, what do? We have this multi-exponential decay. How much of that can we determine? So the original horizontal approach said, let's just approximate this sum, which might be infinite number of terms. Let's approximate it by a single exponential. And their idea was to constrain the area under the curve to be equal. So they just integrated both sides, set them equal to each other, and that leads then to a definition of this effective correlation time that is the mean correlation time for whatever this expansion was. So sometimes people criticize the horizontal approach by saying it's a single it assumes a single exponential decay. But that's not true. It assumes that the internal correlation function is multi-exponential, and it makes a single exponential approximation to that multi-exponential decay. And the approximation that it chose was to match the areas of the curves, and that meant the definition of the correlation time in the horizontal approach is the mean correlation time for the underlying real unknown correlation function. There are other choices that could have been made. And you have a function, a multi-exponential decay. You have some function, and you're trying to approximate it with a single exponential. Matching the areas is only one of any number of approximations you might have thought of. You could have said, maybe I want to match the initial slope. That would say I want to match the first derivative of the curves. So that rather than integrating both sides here, I would differentiate both sides and then solve for tau sub e. And if you do that, you then get the result. 1 over tau sub e is the average of 1 over tau. So now you have the mean rate. In the Lopari-Zabo approach, you have the mean time. And in this approach, if you match the derivatives, you have the mean rate, 1 over a time is a rate. And it's turned out to be more just the way it turned out. What Lopari-Zabo chose as the most popular, most interesting, etc. Because we tend to be interested in the slower motions. And the average of the times is dominated by the slower times, whereas the average of the rates is dominated by the faster times. And it just so happens we tend to be interested in the slower processes, not the faster ones. But if you go back into the literature, there was a time when both were used. Even in Lopari-Zabo's original paper, they pointed out one could imagine extensions to models that might involve the derivative at the interval, no reason necessarily for limits. So here, for example, it's just some model calculations. This plateau is s squared. I pick 2 exponentials and then calculated what the model-free parameters would be, the single exponential approximation. So here's the real decay, and then green shows the single exponential approximation. So it overshoots here and undershoots here to make the area the same. And when we take the Fourier transformation, what's the relationship between the area under the autocorrelation function and the spectral density function? That's an important thing to know. Let's write the definition of the Fourier transformation. So, in our case, we integrate over tau. So, the integral is that. So how is the integral related to J? Is it related to J at all? Is there some value of J that makes this true? Right? If I make omega equal to 0, then I have this. So the correlation function looks something like this. The Fourier transform ends up looking something like that as a function of omega. But this point at 0 is the area under the correlation function. So that you could say is a wise thing about Lopari-Zabo's choice, because J0 is really important in relaxation because that dominates transverse relaxation. So their definition gets J0 because they require that the integrals match for the correlation function, and therefore the Fourier transform J0 will be correct. So if we plug in the product of the overall coupling and the internal correlation function of Fourier transform, here's the spectral density function that comes from the single exponential approximation of internal motion for a spherical molecule with correlation time positive C. And that is an equation you can use hundreds and hundreds of times. There's the J0. You could imagine adding on more exponentials and now have an internal correlation function that has two exponentials rather than one. And then we can define the amplitudes however we want. And the way this was done by Clore and Zabo was to imagine that there were two internal timescale processes that were timescale separated. So there's some very fast process and then some slower process that they gave correlation times tau f and tau s. And you could have imagined writing this as s squared plus alpha f e to the minus tau f plus alpha s e to the minus tau s, where alpha f and alpha s were just the amplitudes of these two terms. But they imagine that this would dictate the some plateau. The fast time scale would dictate the some plateau that they call SF squared, and then the whole thing was going to decay to S squared. So rather than introducing just some arbitrary A sub F and A sub S, they reworked everything in terms of SF, what they call SF squared and S squared. So that's what we see here. But this is really just the amplitude of the slower process exponential, amplitude of the faster process exponential. And then you can imagine adding on more terms, having three exponentials. The only problem is when you run out of data or ability to fit the data that you have to a given function. So fitting sums of exponentials is one of the very difficult problems for fitting. Exponentials usually have to be separated. Time constants usually separated by significant amounts, say at least a factor of 3 to 5 in order to be able to resolve the fitting process. So it gets very difficult to fit more and more exponentials just because you end up in a situation where you might think you have a 3 exponential decay, you find parameters for 2 exponential decay that fit perfectly well, just because of the nature of fitting exponentials. So here's again some example. Now I pick 4 exponentials, and blue is the exact calculation, red is the single exponential approximation, and then red is the 2 exponential approximation. And the 2 exponential approximation fits pretty well, now I have 4 exponentials in the actual calculation. And this 2 exponential approximation is sometimes called the extended non-discrete formula. When we put it all together, Fourier transform, and here's the expression with respect to density.
That's how many? 3.
Has 3 time constants, overall tumbling, 2 internal time constants, and then 2 order parameters. So it's going to be a lot of data.
Case with 4
Pardon?
dimensional motions?
Well, here I just made a calculation of 4 exponential decay, just to see how well I can fit it with the 1 exponential approximation, 2 exponential approximation. Just to show that even though I get 4 exponentials here, when I fit with the extended model freeform, which has, well, really has 3 exponentials in it, overall tumbling and 2 internal ones. So the blue curve has 1 more exponential, but the red curve fits pretty well. Pardon? Oh yeah, I guess I must be, yes. Oh, here, this is just looking at the internal function. I don't have the overall function at all. 2 versus 4. So the curve has 4 exponentials, and then red is fit with 2.
Yeah, but the next slide.
Yes. But now we have overall function. So the other part of relaxation then is working out these double commuters. So we have to know the spherical harmonics, so here are the spherical harmonics. And again, just to warn you that depending on what text you look in, there can be different normalization factors for the spherical harmonics, so you have to pay attention to that. And then we need to know the C's. So I think you've seen all of these from Ann, the coupling constants for the dipole interaction, chemical shift, anisotropy, and quadrupole. Here are the tensor operators then for the dipole interaction. And now here's an example where we need P. So for example, for Q equal to 0, we have the IZSZ terms, and we also have the zero quantum terms. And we need to keep these separated from each other. And that's done by this variable P, which I just use 0 and 1 here, although I could have used red and blue, it doesn't matter. And similarly here, when Q is equal to 1, we also have to keep track of whether we're talking about the S spin, which has a frequency omega S, or the I spin, which has a frequency omega I. So 0 and 1 don't mean anything for P, they're just placeholders to make sure we separate things. One has to be careful about the omegas because these are sign. So omega for nitrogen is negative because the magneto-gyric ratio is negative. So one has to be careful about making sure you keep the sign of omega when you do this calculation. So for example, the zero quantum frequency for nitrogen hydrogen on a 500 is 550 because it would be 500 megahertz minus a negative 50 megahertz. And the double quantum frequency would be 450, 500 plus a negative 50. So in that case, the double quantum frequency is smaller than the single quantum frequency. I mean, smaller than the zero quantum. So you have to be careful, otherwise errors arise. Here are the tensors then for CSA and quadrupole. And then fortunately for you, your predecessors as graduate students have done all the double commutators. So if one works out all of the double commutators, you end up with expressions for the rate constants that are linear combinations of the spectral density functions at the eigenfrequencies of the spin system. So here are the dipole expressions. So this would be R1 relaxation of the I spin, R1 relaxation of the S spin. Here's cross relaxation between the two, that is the N wheel. Here is relaxation of longitudinal 2-spin order, 0 quantum coherence, in-phase magnetization of the I spin, so R2 for the S spin. Here is relaxation for interphase transverse magnetization of the I spin. And you can see they're dominated by J0, but there are small differences in the other spectral density function. And here double bubble. And now here that this is really what I would have called previously C squared. Now, assuming the distance is fixed, we depend on R minus 6. So this previously, if I was consistent, this would have been called C squared. And we can do the same thing for the CSA and for the quadrilateral. I think I mentioned early on when we did the adiabatic analysis that there was an extra contribution from the limited lifetime of the state in R2, and that could be shown for a two-level system to be equal to 1/2 of R1. And you see that here. Here's the adiabatic part of CSA R2. And this additional part is 3/6, 1/2 D0 times J omega I, which is exactly 1/2 of the R1. So that's a case where you can see that this that's taken place. So far we've only talked about single interactions, say the dipole, but we go back to the N15 case. The N15 spin is relaxed by a dipole interaction with the attached proton and by chemical shift anisotropy of the N15. The dipole tensor is oriented along the axis, the bond vector. The CSA tensor is oriented almost parallel. It's tilted away from the bond by something like 16 plus or minus a few degrees. They're almost parallel. And as the molecule tumbles, both of those orientations change in the same, more or less the same way. If the molecule was rigid, they would have exactly the same time dependence. And that means that the vector sum fluctuation that the N15 sees is always the vector sum of those two interactions. And we can ask how that affects things. So basically, our fluctuating Hamiltonian has to be the sum of all the Hamiltonians affecting a given spin. In this case, this would be a sum of two, the dipole interaction and the CSA interaction. One can imagine a much more complicated situation. If we were to talk about, say, a methyl group and relaxation of a carbon-13, this sum could include the CSA of the carbon-13 plus interactions with each of the three attached hydrogens. Luckily, the CSA is pretty small. In any event, this is relatively simple in theory, because back here in the interaction frame, we just have to replace H1 with the summations. So we pick up a couple of extra summations. But then we proceed from that point just as normal. If we like, we can separate the sum, the double sum, into one sum in which the indices are the same, and then another sum in which the indices are different. This would just be our relaxation due to each individual interaction, and this would be the relaxation from the correlation between interactions, sometimes called cross-correlated relaxation or relaxation interference. But then we go up, continue to do exactly what we did before, just keeping track of the two different sums. And then we end up with our normal relaxation, and then these cross-correlated relaxation terms, in which the spin operators, we have to keep track of which Hamiltonian they came from. One came, say, from the dipole Hamiltonian, the other one came from the CSA Hamiltonian. So we have the sum of that. And then our correlation function becomes a cross-correlation function. How are fluctuations in the dipole tensor related to fluctuations in the chemical shift anisotropy tensor? And that's really the only difference in the formal theory. Here's an example. So let's just look at the adiabatic part to make our life easy. We go back to the tables for adiabatic part of T2. We just want the parts along Z. So here's the Z part of the dipole tensor. Here's the Z part of the chemical shift anisotropy tensor. They're oriented in the molecule with some angle beta in between them. The total Hamiltonian is the sum of the two. And then we can just plug this into our equations, calculate the double commutators, and we're done. But let's go back to our random phase model. And I remember what I mean by XZ is the identity operator for the I spin times the S spin, Z operator. And the identity operator is the sum of I alpha and I beta. And here, IZ is the difference between I alpha and I beta divided by 2. So I made those substitutions. Again, it's a case of me knowing the answer. So when I make the substitution, I then see I have two terms, one in which the two tensors add up, and one in which the two tensors subtract. One of them is associated with I alpha SZ, and the other is associated with I beta SZ. And after I puzzle around for a while, I decide for myself what this means is that this is the fluctuation sent by the doublet component with the hydrogen in the alpha state. And this is the fluctuation experienced by the doublet component where the hydrogen is in the beta state. So that I can calculate two separate rate constants. So for one doublet component, the fluctuation on Z is the sum of the two, and for the other, the fluctuation on Z ends up being the difference of the two. And then we remember that our expression, adiabatic expression, was the average squared fluctuation times the correlation. So I just have to square these and average them. So I've done that here. I have a little bit of an issue that now, for the dipole tensor, I have theta orienting the bond vector, but for the CSA tensor, I have theta orienting the CSA tensor. That's not much of a problem here, but it's a bit of a problem here. frequently people just assume that beta was 0 and ignore the problem. But if we want to take beta into account, we know what to do. We have to transform one of these into the frame of the other using the beta rotation matrices. So that's done here. And the algebra is in the notes. So I won't go into that. So we end up with, for the alpha doublet component, an expression here. This is just the relaxation due to the dipole interaction, relaxation due to the chemical shift in isotropy, and then a term that reflects the correlation between those two. And for the other doublet component, we end up with the difference. And then one of these terms subtracts and the other adds. It depends on the relative signs of C and D. Right? If C and D have the same sign, then this is negative and this variance is smaller than this variance. So we end up with the normal dipole relaxation added to the normal CSA relaxation. And then there's this so-called cross-correlated relaxation that adds to one of the doublet components and subtracts from the other doublet component. And that's the Trozian effect. And as we make the magnetic field bigger and bigger, C gets larger, but D is independent of the field. So our hope is to find a field where C and D cancel each other so that the line becomes very narrow. And here's just an example of the simulation that I did. So orange is omega for the CSA as a molecule is tumbling. Green are the fluctuations due to the dipole tensor as the molecule is tumbling. This is at 900 megahertz, so they're nearly matched. And then the difference between them is very small. For that doublet component, relaxation depends on the variance in the black curve. And the line will be narrow. Even though the individual Hamiltonians are fluctuating like mad, their difference is barely fluctuating at all. And therefore relaxation will be reduced. The other doublet component is going to be the sum of these two. The fluctuations are twice as big as any individual fluctuation. Squared, the relaxation is going to be 4 times larger than the individual relaxation rate constant. The line is going to be really broad. And for big enough molecules, you don't have to do anything to get the Trozian effect. You just have to not decouple, and then the broad line is gone. It's so broad, you only do see the narrow line. And here's an effect. So this assumed that the two had beta of 0, and here I assume beta was 15, and then the matching isn't so perfect. So you can see the variance is going to be a little larger. So at 900, you don't get a good match. So there's a lot of debate over what the optimal field is. Here's a picture of just an HSQC. This is a 50 kilodalton protein. So there's this Trozian effect in both dimensions. One piece of evidence that God is really an NMR spectroscopist is that the Trozian effect on the amide hydrogen is almost the same as the Trozian effect on the amide nitrogen. And that's because the frequencies are 10 times larger for the hydrogen But the CSA is about 10 times smaller. So the chemical shift anisotropy coupling constant is about the same size for the hydrogen as it is for the nitrogen, and the dipole coupling is obviously the same. So that's fortuitous. So here's the case where we have the narrow doublet component in both dimensions, and there's a very strong peak. Here we have the narrow doublet component for the hydrogen dimension, but the broad doublet component for the, this must be narrow for the nitrogen, broad for the hydrogen. Here we have narrow for the hydrogen, broad for the nitrogen, and here both are the broad component that is basically completely gone. This is, I think it's 600, so it's not even near the optimal view for this. If we were to decouple to do a normal HSQC, we would end up with a peak in the middle that was basically the average of these. And you can see that's a pretty silly thing to do. We're averaging in basically noise. And the Trozy experiment says, let's just keep this one. Now, if the protein isn't big enough, we have to put in some pulse sequence elements to filter these two out. So that costs a little bit of time. So it's really a remarkable experiment. And Redfield knew this. It's a very funny part of science. In about 86, maybe, Hawkins, Redfield, Griffey. You remember it? Hawkins with Griffey? Griffey and Redfield wrote a review article about the inept experiment, and basically said because of this effect, you could, in some situations, gain signal to noise and double the depth to the experiment. But they just wrote this in this review article, never did the experiment. And that sentence just sat there for 6 or 7 years until Wickard and Verhoeven actually invented the Trozy experiment. As far as I can tell, neither of them knew about the Griffey and Redfield paper. But as soon as their paper came out, I said, wait a minute, I've read this somewhere, and went back to the Redfield paper and thought, oh my God, anybody who read the Redfield paper could have done this experiment. None of us did. So, I don't know what the moral of that story is.
Careful what you write, careful what you read.
I think it's mostly that Redfield knew a lot of things. The notes go through, then the methyl Trozy. It's kind of a lot more. I'll just yeah, so maybe we're at a good stopping point. You can look at the methyl Trozy part, just the one lot of algebra to show that the methyl Trozy experiment works on some very clever balancing of effects. So we're done at this point with Redfield theory. So fast unit processes, Redfield theory is complete. The question is what happens if we don't have these fast unit processes, or the slower conformational processes like motions, protein folding, opening and closing of clamshells. As I said, keeping higher order terms in the Taylor series expansion doesn't work because once the next term is large, they basically are all large, converting this is going to move slow. So we need another theory. As you'll see, this quickly end up being computer calculation at the end of the day. But that's what our next time in solution and picking solids is on one rubric chemical exchange or conformation exchange. And for many years, these were annoyances in solution and more or less ignored, or people trying to get rid of these. And now they're one of the most interesting parts of NMR, or because they allow you to measure properties, slower conformation processes in so that's the next lecture. Mike, did I send you this lecture?
I don't know either.
Okay. I will send it to Mike and I'll send the next one at the same time, so if you want to look ahead. And I think next time, in the beginning, Anne is going to talk about some of the differences between solution and solid state relaxation. Because obviously in solids, you don't have a local number, which is a common effect in solution. Upcoming, for those who are taking the course for grade, is the final paper. And the final paper, I think we can maybe do the last day of this exam. I'll double check what that date is and email it out. The papers in the past have been 5 to 10 pages, double spaced. And we like it if it's not exactly your thesis topic, in NMR. Most of the papers have been an analysis of, say, some whole sequence paper explaining how it works, or have been mini review, some application of NMR